Just over a week after the copy file release, we now have two new CVEs and a new exploit release called Dirty Frag. Dirty Frag is very similar to both Dirty Pipe and copy fail. In copy fail, the danger was smuggling page cache memory into a crypto write via a crypto scatter list. With Dirty Frag, the danger is again smuggling page cache memory into a kernel write via a network packet. Before we start, there are two concepts to understand: page cache and splice. I covered both in my copy fail video, so go back to that one first if you need a full explanation. The short version is this: the page cache is where the kernel keeps cached file data in memory. Splice lets that file memory move into pipes and sockets without copying the bytes. Instead of the socket getting its own private copy, it can end up holding a reference to the same cached file page. Think of it as a direct pointer to kernel memory containing sensitive file data we have read access to, like root-owned configuration files. The core issue is Splice can attach cached file memory to a network packet. The packet contains memory that came from the page cache, but the crypto code thinks it's just normal packet data. So when ESP or RxRPC decrypts the packet, it writes directly into that page cache location we provided. Let me explain how this exploit works for ESP first. Here we have the ESP network packet. The SPI is the 32-bit value that selects the XFRM security association. The attacker installs multiple SAs through Netlink ahead of time, each with a different SPI and a controlled seek high. The seek field is seek low. In the exploit, it is set to 200, so the packet survives XFRM replay checks and reaches the crypto path. The 0xCC bytes are padding. The ESP is using AES-CBC, so the cybertext needs 16-byte block alignment. These bytes shape the packet. The decrypted value does not matter. The final 16 bytes are the important part. They come from Splice, so they are not copied packet memory. They are an SKB fragment that still points back into the target file's page cache. The attacker controls seek high by installing the security association. The exploit fires, installs 48 security associations, each with a different SPI and a different seek high, carrying the next 4 bytes of the payload. It then fires 48 packets and gets 48 4 bytes writes, overwriting 192 bytes of the target file via the kernel with shellcode. Here is the issue. The UDP path failed to mark this spliced fragment with skb fl_shared frag, so ESP does not know it needs a private copy. ESP input reaches the crypto path and runs in place on the skb frag. But that frag is actually cached file memory, so the write lands in the page cache. Now, for demonstration purposes, the ESP path could have simply written 4 bytes to etc password to gain root, just like copy fail. The full ELF overwrite using 48 iterations over BIMSU was simply the exploit author showing off what the vulnerability is capable of. There are some limiting factors to this, which I will go over at the end, but let's move on to the RxRPC vulnerable path first. Dirty Frag performs a brute force of a session key to overwrite the target file. Here is how that works. The exploit collects everything it needs from public sources: the epoch, SID, call number and service ID from the RxRPC handshake, plus the 8 spliced bytes from etc password at the target offset. All of this is obtainable without any privileged access. The brute force then runs entirely in user space. It loops through candidate session keys, running fcrypt decrypt against each one until the output matches the desired plaintext. Once the right key is found, It's planted directly into the kernel keyring. The kernel will now use that exact key when processing the incoming packet. This happens 3 times across overlapping offsets to ensure the full target region of /etc/password is reshaped correctly, removing the root password entirely. There are limitations though. The ESP path requires the ability to create XFRM security associations, which means the exploit needs access to cap-net admin inside a network namespace. In practice, that usually means unprivileged user namespaces have to be enabled so the attacker can create a private net namespace and gain network admin capabilities locally. The RxRPC path is different. It does not rely on XFRM state installation, but it does depend on the RxRPC and RxCAD kernel paths being present and reachable. Not every distribution ships those components enabled by default. So, to wrap this all up, Dirty Pipe showed us page cache corruption through pipe buffers. Copy fail showed us the same idea through crypto scatter lists. Dirty Frag moves the exact same primitive into the network stack itself. There is a good chance this isn't the last we hear of this style of vulnerability. Hopefully this video helped you understand this new exploit, and I'll see you in the next one.